Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Okay, I want you to do something for me right now.
Oh boy.
It might feel a little bit odd, especially if you're, on a crowded train or sitting in an office, but just humor me for a second.
All right, I'm listening.
I want you to look at the space right in front of your face.
We're starting with a staring contest with the air.
Stick with me here. If you're driving, just glance at the empty passenger seat. If you're at home, look at the gap between you and the wall.
Okay, focusing on the nothing.
Exactly. Focus on that empty space. And I want you to really ask yourself, what are you seeing?
Well, broadly speaking, most people would say they're seeing nothing.
Right.
Maybe some dust motes if the light is hitting it just right.
Sure.
Maybe some air molecules if they're thinking scientifically. But mostly, empty space.
Exactly. Nothing. A void. That's the intuitive answer, isn't it?
It is.
That's what our eyes tell us. And frankly, that's what our brain wants us to believe because it's simple.
The world is simpler if a box can just be empty.
But here's the hook. And honestly, it is one of those things that has been keeping me up at night since we started reading the source material for what we're talking about today, that nothing. It's a complete illusion.
It is indeed. And not just, a visual trick. We're talking about a fundamental misunderstanding of the very nature of reality.
And we're going to talk about a study today that just fundamentally shatters that illusion.
It really does.
It turns out that what we think of as a vacuum absolute emptiness is actually a chaotic, bubbling, violent, high-energy soup.
It's teeming with activity.
And we aren't just talking about random noise here.
Yeah.
We're talking about the fundamental building blocks of reality.
Blinking in and out of existence faster than you can even comprehend.
Right. And for the longest time, for decades, really, this was just theory.
It was math on a chalkboard. It was something physicists told each other to make the equations balance out.
But we have a source today, a brand new study published just yesterday, February 4th, 2026, in the journal Nature, that changes the whole game.
It's a significant milestone. It's one of those papers that I think people will be citing for a long, long time.
Because scientists have found a way to essentially glimpse this hidden world. They have watched nothing turn into something. They have tracked how visible matter, the stuff you and I and this microphone and your headphones are made of, emerges from that empty void.
It sounds like science fiction.
It really does.
It sounds like something out of a metaphysical philosophy book, but it is very real, hard-nosed experimental physics.
So let's set the scene before we get into the mind-bending details. This news comes from the U.S. Department of Energy's Brookhaven National Laboratory.
And specifically, a group called the STAR Collaboration.
Right. And for context, when we say collaboration, we aren't talking about 3 people in a garage lab.
No, not at all. We're talking about hundreds of physicists from institutions all around the world.
And they're working with one of the most impressive machines human beings have ever built.
The Relativistic Heavy Ion Collider, or RHIC.
A particle smasher.
A particle smasher, yes, but on an incredible scale. It's a massive facility designed specifically for nuclear physics research.
And their mission, the mission we are going to explore today, is honestly audacious.
It really is.
They're using subatomic car crashes, smashing particles together at unbelievable speeds to turn virtual ghosts into real, solid matter.
And the stakes here are incredibly high. This isn't just about cataloging some new, obscure subatomic particle that, no one outside a lab cares about.
Right.
This is about understanding the fundamental origins of mass. It's about understanding the structure of the universe itself.
And as we'll find out later, it even connects to the future of computing.
In a very direct way.
But we'll get there. First, let's unpack this illusion of nothing. Because to understand how they turn ghosts into real stuff, we have to understand what the vacuum actually is.
We have to redefine empty.
You agreed with me earlier that nothing is a lie.
That's right. It is.
But historically, we didn't always think that, did we? I mean, if you asked Isaac Newton what a vacuum was, what would he have said?
Oh, he would have said it's an empty stage, a void. A container where absolutely nothing exists. And for a long, long time, that was the prevailing view in science.
The common sense view.
Exactly. But this isn't exactly brand new information for physicists. The source material mentions that physicists have known for about 100 years that the vacuum isn't truly empty.
100 years. So we've been living a lie for a century.
Give or take. Really, since the dawn of quantum mechanics. The classical idea of a vacuum, that perfectly empty box, just doesn't work when you get down to the subatomic level. Quantum mechanics came along and, well, it ruined the simplicity.
It always does.
It does, and now we understand the quantum vacuum.
The quantum vacuum. It sounds like a cleaning product from the year 3000?
It's significantly messier than that, and honestly, a lot harder to clean up.
So what is it?
The quantum vacuum is filled with fluctuating energy fields. You can't get rid of them. They're a fundamental property of the universe.
So even if I took a box, pumped out all the air, all the atoms,
every single atom, every photon, every bit of radiation from that box, and you shield it with thick lead, and you cool it to absolute zero.
the lowest possible temperature.
Those fields are still there, buzzing with energy.
But why? Why can't we just have zero? It seems like zero should be an option.
Because of the Heisenberg uncertainty principle?
Okay, I've heard of that. That's the you can't know exactly where something is and how fast it's going at the same time rule.
Exactly, but it's a bit broader than that. It also applies to energy and time.
How so?
You cannot know the exact energy of a system for a specific, precise amount of time. If you say, this box has exactly zero energy for all time, you are claiming to know its energy perfectly.
Which violates the principle.
Which violates the principle. Nature forbids absolute zero energy. There must be fluctuations, a little bit of uncertainty, a jitter.
So the universe forces a little bit of wobble just to satisfy its own rulebook.
Precisely. And these energy fluctuations, they aren't just abstract numbers. They manifest as what we call virtual particles.
Virtual particles. Okay, this is a key term for our whole discussion. I want to make sure we really get this concept down.
It's central to everything.
So what exactly is a virtual particle? Is it real?
It's complicated. Think of them as entangled pairs. Matter and antimatter.
So a particle and its opposite.
A particle and its antiparticle counterpart. For example, an electron and a positron. They spontaneously pop into existence, borrowing energy from the vacuum.
Okay.
And then almost instantly, they snap back together and annihilate each other, paying the energy back.
So they appear out of nowhere and then disappear.
Exactly. They blink in and out of existence.
How fast are we talking? A second, a millisecond?
Much, much, much faster. We are talking about timescales so short that they are almost immeasurable.
So short that they're almost not even there.
In fact, they exist on such short timescales that, according to the laws of physics, they are never counted as real matter. They don't stick around long enough to be detected by standard means.
So they don't trigger a Geiger counter. They don't leave a trail in a cloud chamber.
Nope. They live and die in a time so brief they can't directly interact with our world. They are a constant, invisible fizz.
So they are like ghosts.
Yeah.
They're there, haunting the vacuum, but they aren't really interacting with our world.
Ghosts is a pretty decent analogy, yes. But I actually prefer the analogy you alluded to earlier.
The boiling soup.
The boiling soup analogy, yes.
Yeah.
Let's break that down.
Okay.
Imagine a pot of really thick, viscous soup on a stove. It's simmering right on the edge of boiling. Even if you look at a patch of the soup where there are no ingredients, no carrots, no potatoes, the surface itself is still moving. It's frothing.
Right. You get little bubbles forming and then plopping almost immediately.
Exactly. You have these tiny bubbles constantly forming on the surface and then popping right away. The surface is never truly still.
So that's space. The bubbles are the virtual particles.
That is space. It isn't a void. It's a bubbling soup of potential energy that's just waiting to be realized. The bubbles are the virtual pairs.
So everywhere I look, in the empty air in this room, in deep space between galaxies, inside my own skull, there are these matter-antimatter pairs popping up and destroying each other constantly.
Constantly. Trillions upon trillions of times a second in every cubic centimeter of space.
That's just overwhelming to think about. It makes the universe feel very crowded.
It is crowded. The vacuum is the busiest place there is. This is the bedrock of what we call quantum field theory.
Okay, but here's the problem I'm having. If they annihilate so quickly, they stay virtual.
Right.
They're potential matter, not real matter. They're bubbles that pop before they can float away.
Correct.
So how do we make them real? How did the folks at Brookhaven turn these soup bubbles into something that doesn't just pop? That's the big news here, right? They didn't just theorize about the soup. They actually cooked with it.
That brings us right to the experiment itself. To turn virtual into real, you need to pay a toll.
A toll. Like a bridge toll.
Exactly like an energy toll. Remember, nature has to balance its books. The law of conservation of energy is absolute.
Can't create something from nothing.
You can't just create matter out of nothing for free.
Yeah.
These virtual particles are borrowing energy from the vacuum for a split second, and then they pay it back by annihilating. The books are balanced.
Okay, so it's like a tiny, super fast loan.
A perfect analogy. But if you want them to stay, if you want them to become permanent, real particles, you need to step in and pay that energy debt for them.
So you cover their loan.
You inject enough energy into that system right at that spot to rip those pairs apart before they can annihilate each other. You give them such a boost that they can fly away and never have to pay the debt back.
And that's where the relativistic heavy ion collider comes in. That's the bank.
Exactly, the RHIC. This machine is designed to deliver that massive energy paycheck.
So describe the mechanism. What are they actually doing at this facility to pay this toll?
They are performing proton-proton collisions. So they take protons, which are the positively charged building blocks of atomic nuclei.
The stuff we're all made of.
And they accelerate them around a 2.4-mile ring.
2.5 miles? That's huge.
It is. They use thousands of massive superconducting magnets to steer them. And they get them going fast.
Oh, fast.
99.999% the speed of light.
So basically as fast as the universe allows anything with mass to move.
For all intents and purposes, yes. They are pumping these protons full of an incredible amount of kinetic energy and then
smash.
A head-on collision.
Yeah.
A catastrophic collision at the subatomic scale.
And that releases all that energy they built up.
It releases a tremendous amount of energy in a tiny, tiny point of space. We are talking about temperatures and energy densities that haven't existed in the universe since the first microsecond after the Big Bang.
And that fireball of energy is the boost. That's the payment for the loan.
Precisely. That fireball of energy permeates the quantum vacuum right at the collision point. It floods those ghosts, those virtual particles, with so much energy they are ripped apart and become real.
I like the way the source describes it. It says, the collisions deliver an extra energy boost that transforms such virtual particles into real particles. It's so clean.
It is. Going back to our soup analogy, it's like cranking the heat up on that pot so high that the bubbles don't just pop on the surface.
Right.
They get enough energy to break free entirely and become droplets of steam that fly away. They become persistent. They enter the real world.
Okay, so we have smashed the protons. We have dumped a ton of energy into the vacuum. We have popped these virtual particles into reality.
Yes.
But here's the catch, and the source makes a big deal about this. A particle collision is an unbelievably messy place, isn't it?
Extremely messy. Messy is a profound understatement.
It's not like just one pair of these new particles pops out and waves at the scientists.
No, not at all. When you smash protons at relativistic speeds, you create a shower of debris. The protons themselves break apart into their constituent quarks and gluons.
And all that kinetic energy gets converted into new particles.
Exactly. Through Eamsia forticum, you get quarks and gluons flying everywhere. New particles are being created from the pure energy. Millions of particles can be created in a single one of these events.
A storm. A chaotic storm of matter and radiation.
That's a very good description.
So this is my question. If you have millions of particles flying out from the center, how in the world do you find the specific ghosts you are looking for?
A very good question.
It sounds like trying to find a specific special raindrop in the middle of a hurricane. How do you know this particle came from the vacuum and that particle came from the proton itself?
That is the core challenge of detection. First, you need an incredible camera, and that's the star detector.
The star detector. I've seen pictures of this thing. It looks like a giant cylinder the size of a house, just packed with wires and electronics.
It is. It stands for Solenoidal Tracker at RHIC. It's essentially a giant digital camera that surrounds the collision point.
And it tracks everything.
It captures the tracks of these thousands, sometimes millions of particles flying out from the collision. It measures their speed, their charge, their trajectory, their momentum. It builds a 3D picture of the explosion.
But again, if there are millions of particles, the detector just sees a giant mess, a beautiful, complicated mess. How do they filter it?
That is the crucial question. And that leads us to the real detective work of this study. They couldn't just look at the photo.
Right.
They needed a specific clue, a tracer, something that would act like a dye pack, distinguishing a vacuum particle from a regular run-of-the-mill particle.
Okay, so this is where the cleverness comes in. They didn't just look at any particle. They looked for something very, very specific.
They did. They focused on a type of particle called a lambda hyperon.
Lambda hyperon. It sounds like a fraternity from a sci-fi movie. Lambda hyperon.
It does. And crucially, they also looked for its antimatter counterpart, the anti-lambda. They looked for them in pairs.
Okay, so why these? Why not just look for electrons or regular old protons? Why go hunting for something so exotic?
Because lambda particles contain a very special ingredient. A strange quark.
A strange quark. Now, I love physics nomenclature.
Yeah.
Strange is the actual technical name, right? They're not just being poetic.
It is. In the standard model of particle physics, we have 6 flavors of quarks. You have up and down, which are the, let's say, boring ones.
Hey, don't insult up and down quarks. I'm made of them. You're made of them.
We all are. That's my point. Protons and neutrons are made of up and down quarks. That's the vanilla and chocolate of the universe. It's the stable, everyday stuff.
Okay.
But then you have their heavier, more unstable cousins, charm, strange, top, and bottom.
Right. So the lambda particle contains a strange quark, and the anti-lambda contains a strange antiquark. Why is that the key?
Because the protons you are smashing together, they are made of up and down quarks. They do not contain strange quarks.
I see where you're going, the ingredients list.
Exactly. If you smash 2 things together that have no strange quarks in them, and suddenly you see a strange quark flying out of the explosion.
You know, it was created fresh. It wasn't just luggage that the protons brought with them to the crash.
It had to be manufactured right there on the spot.
Okay, so that narrows down the search field immensely. That's a huge filter.
It is, but even that isn't quite enough.
Why not?
Because you can create strange quarks just from the pure kinetic energy of the crash. You can transform motion into mass into a strange quark-antiquark pair. That doesn't necessarily prove it came from a virtual vacuum fluctuation.
Okay, so we're getting closer, but we're not there yet. We need another clue. A fingerprint that says, I came from the vacuum soup, not just, I was made by the energy of the crash.
Correct. And that final definitive fingerprint is a property called spin.
Spin. Okay, every time we talk physics, spin comes up, and it's always a little bit confusing. We aren't talking about a tiny particle spinning like a top, are we?
Not literally, no, though the mathematics is similar, which is where the name comes from. Spin is a built-in intrinsic quantum property.
Like charge or mass.
Exactly like charge or mass. It's related to angular momentum and magnetism. But for our purposes today, you can just imagine it as a tiny arrow attached to every particle, pointing in a certain direction.
A little compass needle.
A little compass needle. Every particle carries one.
Okay, so I have a virtual strange quark and a virtual strange antiquark popping out of the vacuum soup. And you're saying their arrows, their spins, interact in a specific predictable way.
Yes. The source explains a fundamental rule of quantum field theory. Strange quark-antiquark pairs generated as virtual particles in the vacuum are always spin-aligned.
It's being aligned, meaning their little arrows are pointing in the same direction.
It means their quantum states are correlated, they're entangled from the moment of their birth, they act as a single coherent unit, their fates are linked.
Okay, got it. Now contrast that with a regular messy collision. If I just smash 2 protons together and all that energy randomly creates some strange quarks, what are their spins usually like? Random. Absolute chaos. If you look at the vast majority of particles emerging from a RHIC collision, their spins are randomly oriented in every possible direction. There is no coordination at all. It's just thermal noise.
I see the logic now. This is brilliant. It's a sorting mechanism.
Exactly. The hypothesis was this. If we can find lambda and anti-lambda pairs emerging from the collision that are spin-aligned, it is highly, highly likely that they didn't just bump into each other randomly in the debris field. It proves they originated directly from one of these pre-aligned, entangled virtual vacuum pairs.
The alignment is the proof of origin. It's like finding 2 people in the middle of a massive chaotic riot who are perfectly, flawlessly dancing the tango.
That is a fantastic analogy, yes.
You know they came together. They didn't just meet by chance.
Yes. If you see the tango in the middle of a mosh pit, you know those 2 are linked.
So instead of trying to track every single piece of debris, they're looking for this one specific telltale synchronization.
Yes. They are hunting for a signature of order within the overwhelming chaos. So the billion-dollar question, did they find the tango dancers?
Let's get into the discovery. Because yes, they did. And the results are, frankly, staggering.
The quantum twins.
This is where we bring in the human element of this. The analysis was led by Jan Vanek, a physicist from the University of New Hampshire who was working at Brookhaven.
And we really need to appreciate the scale of this work. They didn't just look at a dozen collisions or even 100.
No. The STAR team examined data from millions of individual proton collision events.
Millions.
Think about the data storage alone, terabytes upon terabytes of data, and then think about the sophisticated algorithms you'd need to sift through that to reconstruct every event.
It's like having millions of haystacks, and you're looking for one very specific, perfectly aligned pair of needles in each one.
And they had to be incredibly careful to eliminate biases, false signals, random coincidences that might look like alignment but aren't. Rigor is the absolute name of the game here.
You can't just claim you've peeked into the vacuum. You have to prove it beyond any doubt. And after sifting through millions of these crashes, what was the smoking gun? What did they find?
The result was stunning. They found that when a lambda and an anti-lambda emerge from the collision close together.
Define close together. How close are we talking?
Physically close in space as they fly out from the collision point into the detector. When they are neighbors, so to speak, in that expanding debris field.
Yes.
They are 100% spin-aligned.
Wait, 100%?
That is what the data indicates. A perfect correlation.
I feel like we need to pause on that number for a second.
Please.
In biology, in sociology, even a lot of other physics experiments, you get statistically significant numbers. You get 80% or 95% confidence. You almost never hear 100%.
It's a statement.
It is a definitive, absolute statement.
It's a perfect signal. It mirrors the exact theoretically predicted state of the virtual quark-antiquark pairs in the vacuum. It tells us that the correlation isn't just strong, it's perfect.
So let me just restate this to make sure I'm getting the full gravity of it.
Go ahead.
They smashed protons. A flood of energy poured into the vacuum. A virtual pair of strange quarks, which were just a possibility a nanosecond before, got promoted.
Boosted into reality.
They became a real lambda and a real anti-lambda particle. And because their spins are 100% aligned, we know for a fact they are the same entangled pair that was hiding in the vacuum soup.
Precisely. It is, as Jan Varick put it in the source, as if these particle pairs are quantum twins.
Quantum twins. I love that imagery. It's perfect.
The implication is just profound. It means the quarks, which are now trapped inside two separate distinct particles, somehow retained the spin linkage that was established in the vacuum before the particles even fully formed.
That breaks my brain a little bit. The connection was made when they were nothing but a flicker of potential energy.
Yes.
And that connection survived the violent birth of becoming something real.
Yes. Shadming, too, another SNAR physicist and a co-leader of the study, called it a unique window into vacuum fluctuations. It proves that the spin alignment, that delicate quantum state, survives the violence of the transformation from virtual to real.
So we are literally seeing the memory of the vacuum stamped onto real matter.
That is a beautiful way to put it. The memory of the vacuum. The matter remembers exactly where it came from.
But there was a condition you mentioned, a really important one. You said, when they emerged close together.
Yes. This is where the plot thickens, and where the story gets, in a way, a little tragic for our twins.
Tragic. How so?
Well, why does proximity matter so much?
This leads us into the next part of our discussion. Entanglement and the breakup.
Right. We need to talk about entanglement properly.
We hear that word a lot in pop science, spooky action at a distance and all that.
Yeah.
What does it mean in this context?
In this study, it refers to that quantum linkage we've been talking about. The properties of the two particles, specifically their spins, are inextricably connected.
So you can't describe one without the other.
Exactly. They're a single quantum system, even if they are two distinct particles flying apart.
Like the twins. They're distinct people, but they share a fundamental deep connection.
Even deeper than that. It's like having two dice that are magically linked. If I take one to London and you take one to Tokyo and I roll a 6.
I roll a 6 instantly.
Instantly. That is the classic idealized view of entanglement.
But this study found something interesting when the twins get separated by too much, right?
They did. This is the other half of the discovery. When the lambda and anti-lambda pairs emerged farther apart in the detector.
So not neighbors in the debris field.
Right. The 100% spin correlation disappeared.
It vanished.
It dropped off drastically. They were no longer aligned. Their spins became random, just like all the other debris in the collision. The tango was over.
Oh, I thought the whole point of entanglement was that it persists over distance. Spooky action at a distance.
In a perfect isolated universe, maybe. If they were the only two things in existence, they would stay entangled forever, no matter how far apart they got.
But they're not in a perfect universe.
They are born in the aftermath of a subatomic car crash.
Right. The hurricane.
Exactly. They are surrounded by other quarks, gluons, photons, intense magnetic fields. It is an incredibly noisy, crowded, and chaotic environment.
So what happens to them as they fly through it?
Jan van Eck explains it by saying that twins sent far away are affected by other things in their environment. They get jostled.
Air pressure.
In a way, yes. As they travel through that debris field, they bump into things, they interact with other particles, with fields, and every single one of those interactions is a measurement in quantum terms.
And a measurement forces a quantum system to choose a state, right?
Yeah.
It collapses the wave function.
It forces them to decohere. The constant noise of the environment effectively washes out that delicate quantum connection.
They forget their twin.
They forget their twin. They become just regular independent particles, each with its own random spin. Their shared memory of the vacuum is erased.
So the environment itself breaks the entanglement.
Exactly. And this is a profoundly important concept. This loss of connection, this decoherence, represents the boundary between the quantum world and the classical world.
The quantum to classical transition. I feel like this is one of the biggest, deepest mysteries in all of physics.
It is. In the quantum world, things are entangled, fuzzy, probabilistic. A particle can be in multiple states at once.
And in the classical world, the world of chairs and tables and planets and podcasts, things are defined and separate.
My coffee cup is here, and it's not anywhere else. I don't feel entangled with it.
Right. And we usually think of those as two totally different realms with different rules. But this experiment is actually showing the transition happening in real time.
It gives us a way to study it directly. We are seeing the moment where the quantum weirdness gets washed out by the environment and becomes normal matter. We are literally watching the magic fade.
Why does that matter outside of just, abstract physics? Does this have any real-world application, or is it just really cool philosophy?
Surprisingly, yes. It matters enormously for technology, specifically for the future of quantum computing.
Really? How does a giant particle collider help someone build a quantum computer? Those seem like they're at opposite ends of the size and energy spectrum.
They are, but they're governed by the same rules. Think about what a quantum computer needs to work.
It needs qubits, quantum bits.
Right, and it needs those qubits to stay entangled with each other. That entanglement is the source of a quantum computer's immense power.
Okay.
But the single biggest challenge in building a working quantum computer is keeping those qubits entangled. They are incredibly fragile.
The environment gets in the way.
The slightest bit of heat, a stray magnetic field, any noise or vibration from the outside world can interact with them, and the entanglement breaks. We call it decoherence.
That sounds exactly like what happened to the quantum twins when they got too far apart in the debris field.
It is exactly the same physics. Zhu Deming, too, pointed this out explicitly in the source material. He said the physics of this transition is the same whether you are studying particle collisions or trying to develop stable quantum hardware.
So by studying how these lambda hyperons lose their connection inside a particle collider, we might learn how to better protect the qubits in a quantum computer from losing theirs.
Correct. It's all about understanding how the environment destroys quantum correlations. If we understand the mechanism of the breakup in this violent high-energy system, maybe we can figure out ways to shield against it in a delicate, low-energy one.
That is just fascinating. It connects the smallest, most violent explosions in the universe to the most delicate, futuristic computers we're trying to build.
Physics is interconnected like that. The fundamental rules are the same everywhere you look.
Let's zoom out a bit. We've talked about the vacuum, the collision, the twins, and the breakup. But there's a bigger picture here. You mentioned mass and the universe.
This is where we get philosophical again, but with data to back it up.
The source mentions reverse engineering the universe. That sounds ambitious.
It is. But think about the Big Bang for a moment.
Okay.
In the earliest moments of the universe, everything was an incredibly hot, dense, high-energy soup. There was no solid matter as we know it, just a plasma of free-roaming quarks and gluons.
The ultimate vacuum soup.
Exactly. But as the universe expanded, it cooled down. And as it cooled, those quarks had to transition. They had to group together to bind to each other to form protons, neutrons, and eventually atoms.
They had to freeze out of the plasma and become the matter we see today.
Exactly. And one of the central mysteries in physics is how exactly does that process of hadronization happen? How do quarks go from being free-moving, entangled entities into these tightly bound, stable, solid particles with mass?
And this experiment sheds light on that.
It does. By creating these particles from the pure energy of the vacuum, we are recreating a mini version of that primordial process. We are watching it happen in a controlled environment. We are reverse engineering matter formation. collision.
So we are watching the recipe for the universe being cooked, one collision at a time.
Yes. And it connects directly to the origin of mass. Most of the mass of a proton, for instance, doesn't come from the mass of the quarks inside it. It comes from the energy of the strong force binding them together.
So we're seeing how that energy gets locked into the structure of a particle.
We're getting a new window into that process. And the source also mentions that they want to study this in even more complex systems, not just proton collisions.
Right. They can collide bigger things.
Exactly. Protons are relatively simple, but they can smash gold nuclei into each other, or lead nuclei, and they want to see what happens to the twins in those environments.
There was a great analogy in the text about growing up.
Yes, to use that analogy, he said we can send these virtual pairs through different environments, different types of atomic nuclei, to see how they grow up.
So if I create these quantum twins inside a dense gold nucleus versus a less dense proton, do they turn out differently?
Exactly. Does the incredibly dense environment of a gold nucleus break their entanglement link faster? Does it affect how they form? It's like studying if a child grows up differently in a crowded, busy city versus a quiet, rural village.
And that tells us how matter behaves in the complex, messy, real world, not just in a simple collision.
Correct. It helps us understand the structure of the nucleus itself. It's like we're using these twins as tiny probes. We're probing the nuclear environment by seeing how that environment changes the probe.
Looking ahead then, what is next? We have this amazing result, but scientists are never satisfied.
No, they aren't, and they shouldn't be. The STAR detector is doing incredible work, but Brookhaven is already in the process of building something even bigger and better.
The Electron-Ion Collider, or EIC.
The EIC.
I've heard of this. It's being built right there, using the existing RHIC infrastructure, right?
Yes. It's the next evolution of this kind of physics. The source calls it a sharper tool for a reason.
Why sharper? What makes it better or different than what we have now with RHIC?
Well, right now at RHIC, we are mostly smashing protons into protons, or heavy nuclei into heavy nuclei. That's like smashing two very complicated Swiss watches together to try and figure out how they work.
It's messy. Springs and gears go flying everywhere.
Exactly. The EIC will collide electrons with ions, or nuclei, and electrons, as far as we know, are fundamental point particles. They don't have any internal structure.
So it's like using a surgical laser instead of a sledgehammer.
A perfect way to put it. You're probing the complex watch with a very simple, clean, precise tool. You can see what you're doing.
So we can probe the vacuum and the structure of matter with much, much higher precision.
Exactly. It will allow for even more precise imaging of the interior of protons and nuclei. It's going to explore that connection between the vacuum and the visible universe with unprecedented resolution.
The scope described in the notes for the EIC is massive. It says from subatomic components to stars, planets, galaxies, and even people.
It sounds grandiose, but it's true. It's not an exaggeration. Because everything, stars, planets, you, me, is made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of quarks and gluons. And quarks and gluons, well, as we've just spent all this time discussing, they have a deep, intimate, and now observable relationship with the vacuum.
It really does all come back to that fundamental mystery, the connection between something and what we thought was nothing.
That is the core of it. We are usually obsessed with the something, the matter, the stuff we can see and touch, but this research forces us to look at the nothing, to respect the vacuum.
The vacuum isn't just an empty container for the play. It's part of the cast.
It's the source. It is the reservoir of all potentiality from which the cast emerges.
So as we wrap this up, let's just try to synthesize the takeaways for everyone listening. We started this whole discussion by looking at an empty room,
which we now know is not empty at all, but a bubbling, frothing ocean of virtual particles.
And we talked about how smashing protons together at nearly the speed of light is the key to unlocking that ocean.
Providing the massive energy boost, paying the toll to turn those fleeting ghosts into tangible reality.
We discussed the quantum twins, the lambda and anti-lambda particles that come out of the chaos, 100% spin-aligned.
The smoking gun that proves their origin was in the vacuum itself, a direct window into the fluctuations of so-called empty space.
And we learned that this incredible quantum connection is fragile. It breaks down over distance because of the noisy environment.
A process called decoherence, which gives us vital clues about everything from the birth of matter to the future of quantum computing.
The transition from the quantum to the classical, the moment the magic fades into the mundane.
A beautiful way to put it.
So why should the listener care? I mean, apart from it being incredibly mind-bendingly cool.
Because it is their origin story. It's everyone's origin story.
Say more about that.
Look at your hand. Look at the chair you're sitting on. It's made of matter. That matter has mass and structure. That mass didn't just appear out of nowhere.
Right.
The fundamental mechanisms that generate mass, the interactions that bind quarks together into stable particles, these are the very same processes we are now studying in real time at RHIC.
So in a very real way, we're all just stabilized, persistent fluctuations of the vacuum.
We are nothing that has been given enough energy to become something and has managed to stick around for a while.
That's both humbling and a little bit terrifying.
It's the beauty of physics, isn't it? It connects the utterly mundane to the truly cosmic.
I want to leave our listener with a final thought to mull over.
Okay.
We talked about how that quantum link, the entanglement, breaks when the particles get too far apart. The environment washes out the magic.
Yes, the decoherence.
It makes me wonder. If the universe creates matter from the vacuum and reality as we know it, this solid, predictable, classical world, is just the result of all those quantum entanglements breaking down over distance and time.
Go on.
What does the universe actually look like if you could see the connections before they break? If you could see the hidden web of entanglement that connects everything before the environment snaps all the lines?
That is a profound question. Maybe at the most fundamental level, nothing is truly separate. We just perceive it that way because the links have been washed out by the noise of existence.
Is reality just the echo of a broken web?
That is something to ponder on your commute home.
Definitely. Thank you for taking us through this. It's been an incredible exploration.
My pleasure. It's fascinating stuff.
And to you, listening, next time you stare into empty space, remember, it's staring back. And it is very, very busy. Thanks for joining us. We'll see you next time.